Hi all, how are you guys? I hope you all are good. It's been a very long time. We haven't shoot a video. So this would be the last video of the NumPy series, and I hope you guys are enjoying it. It's been very late here. It's Saturday night, 3 a.m. in the morning. But yeah, it's necessary that we come with this. So what I will try to do is I will try to keep this video as much short as possible because we would just practically run through the concepts that we are left with, and then whatever code and all is there that's already there, we can just copy paste and try to understand what is being explained into it. It's not very large part is not left, a very small part of what is left. So we can cover that and then try to wind up the NumPy. So let's start that. So SIMT, that is single instruction multiple data. So that we just go through something like this. So imagine that you have two vectors which are column vectors like 1, 2, 3, 4, and 5. Let's decrease the size of these. Then the one 6, 7, 8, 9. This is since this this. So imagine that these two are vectors and I want to do addition. So first let's go through the code, then right. So imagine that I have a NumPy. So NumPy p dot then p is another NumPy array, p dot array, and let it be 6, 7, 8, and let's see the summation of n, and let's just print. So what we get is the summation of these two arrays, that is 1, 6. So it's just element wise summation is what we are getting. But the operation in NumPy is not performed element wise, but rather in some different way. Now, if these A and B would have been Python, pure Python arrays, so let's just write that as well. So let A be equal to this pure thing, and let's B be equal to this pure thing, and then C is again equal to A plus B. Let's see. Comment what would be the answer of this. So this is something very weird thing in Python. What Python does is it does not performs any element wise operation on this, but rather it appends this B array inside the A array, and you get an array which consists of all the elements that are present in A as well as B. So this is a weird way of Python behaving. And if I want to add these two arrays, then I need to run for loop. And when I run a for loop, what we are actually doing is we would visit this element, and then add each of them. Then in the next iteration, I would visit this element, I would add it with this, and then I would store it in the same location to which these are, right? So that's how it would work. So if we write code for it, that for I in range of length of maybe a, then we will have to write that a of I is equal to a of I. So I'm not using any other array named C to store the summation, but I'm rewriting or overwriting the A array itself plus C of I. Sorry, B of I, C of I. And then if I do this, and then if I print A, then I get the summation of these two arrays, which is nothing but similar to what we got here. So if you see these two results, that is this result and this result, both of them are same. But the point here is, here we are running a loop which is unnecessarily adding a time complexity, which is not faster as compared to this one. So let's go back to our this thing. So what is happening is when I do summation of these two arrays, so maybe I add this up and then I get some value which is equal to, let's copy this same thing. Let's copy, paste it over here, 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 just write, change the values of these, so go to the summation of it. So this first would be 7, then 9, then this would be 11, and this would be 13, and this is 15. This is 15. So this is what is the result. But in NumPy, what actually happens is, so imagine this much data is stored inside a register. So hardware register is something which is responsible for storing data. So basically not storing data, but to perform different operations. So there exists 128 256 bits of registers which are able to store more than 32 bits, because they are 256 bits or 128 bits. So they can store large amount of data, and when I perform any of the operation on them, it is performed directly on the entire block of data that is being present and not element wise. So we know that each of the integer is of 32 bits, but if I have 256 bits, then you can have more number of data, and then when you perform a single operation on it, it is performed on the entire block of memory or block of data and not as element wise. So when you add this in a NumPy array, this entire thing is stored inside the register, which is maybe 128 bits or 256 bits, depending upon what hardware they have. And the similarly, this is also stored in, and when you add it, it's a complete block addition and not specific element wise. But when you use Python, something that happens is like this. So these two would be added, and then you would get a 7. Then similarly, these two would be added. So with this one. This two would be added. Then these two would be added. Then these two would be added. Then these two would be added. And finally these two would be added. So we need to repeat, we need to loop in, or we need to have this loop to run over and then add element wise, which requires more time, right? So we are saving time as well as memory when we are trying to use NumPy in these operations. And that is what is SIMT, which is single instruction but multiple data. So here the instruction is nothing but the mathematical operation that you're performing. In this case, it's addition. So, sorry. I'm not that's what I wanted to say. So maybe, so this is the operation that we are performing, and this is this is a single instruction that we are providing. But when you say multiple data, it means not a single integer, but block of integers, and then it is performing that operation on block of information, not on the single or element of that, or one single part of that block. Okay, so that's what it actually means when we say SIMD. So that's what the SIMD thing is. So if you go through this explanation, it explains the same thing, that instead of CPU doing a simple add, that is element wise addition, it does addition in one instruction cycle as a block of data. So how is this possible? So again, vector registers. There are something called as vector registers, which could be 128 bit, 256 bits, or 512 bits. And these are the instruction sets. So if you guys might, I don't know if you guys know or not, there is an instruction assembly language for 8085, and then that is used to do various operations inside the registers. Okay, and similarly, it has a lot of different set of instructions that are used to perform different operations on them. So similarly, these are the special instruction sets that are used, to perform these kind of operations. Single instruction, multiple data operations. So you can see the calculation over here, that the register size is of 256 bits each, and each number is 12 bits. And if you divide, so you can save 8 numbers in the 256-bit register. So if you want to perform any operation, you can consider that entire block of 8 numbers at the same time, and that's been processed at simply once, and that is 8x speed boosted. Because if you are using a simple Python for loop, then you need to perform the same operation 8 times, but here it is performed at single point of time. So that's why it's 8x faster as compared to the Python loops. Now, this reason we have covered this thing in the previous videos. You can go and watch them again. And then, here it explains the same thing, that why is SIMD extremely important, or what is the use of it, or what is its benefit using it in NumPy. So that's all. So this was pretty much of SIMD. The next part is BLAS, which is basic linear algebra subprograms. Now, when I say basic linear algebra, what does it mean? So we have vector operations, metric operations. What are vector operations? Dot products, cross products, then matrix multiplications, matrix additions, matrix subtractions. Division in matrix does not exist as such. We have inverses in matrices. So calculating an inverse of a matrix. These are all simpler or basic linear algebra subprograms, or linear algebra operations that we perform on vectors and matrices. So BLAS is nothing but the same thing, and so you can consider that BLAS is one layer top, which is built upon SIMD. So SIMD is the core of BLAS. So inside or internally, it uses SIMD. On top of it is BLAS, because BLAS in itself uses SIMD to perform different kind of these operations. So you can say specification standard API. So you can consider it as an API, as we have in backend systems, which is talking to your front end. Similarly, BLAS can be considered as an API which talks to the SIMD in order to perform different matrix multiplications, or not matrix multiplications, but to speak in general, it means that it is used to perform different vector calculations, matrix calculations. Okay, and it has 3 levels of operations. The first is vector operations. What are vector operations? Dot products, vector addition, scalar multiplication. So what is this? I think you all guys know this. So dot product is, for example, let me show. Say, for example, you consider these two are let's first of all get rid of this. So if I do a simple this is sorry. This is a dot product, and the answer that you would get when you do this product is nothing but, so it's element wise multiplication and nothing else. So what you would actually get in here is something like 6, then 14, then 4, 32, and 50. So if we want to try and see what result we get, so the same thing in here, not here, yeah, here. So let's add a cell in here. Then let's write A is equal to A multiplied by B, and try to get D. Do not multiply sequence of, oh yeah, the reason being we declared A and B as these, and then we are running it, so we need to run this again and then run this again. So we got the same answer that we expected. So 6, 14, 24, 36, 50, which is similar to 6, 14, 24. Oh, I'm sorry, I just made a mistake. 36 and 50. So this is nothing but dot product of vectors. Then if you go for scalar, for example, I'm writing 4 in here, then this would be multiplied by 4. And if I want to see the total result onto this, then this entire block would be 4 times. So that's the only difference. So I think makes sense. And then what was the operation? Vector addition that we have already discussed. So this is the example wherein you have, maybe you can consider A as a scalar. So it's a scalar multiplication, or you can consider A as another vector. So it would be a dot product, and then this is additional. Then we have matrix vector operation. So this thing is something which is used in eigenvalues and eigenvectors, which is the next topic again. So after BLAS, we have something called as LAPACK, Linear Algebra Package. Inside that we have eigenvalues and vectors. So to be honest, or to make it more simple, it is nothing but a matrix and a vector multiplication. So also remember that, so for example, if I have a matrix like this, so maybe 3 cross 3 matrix, and I have a vector like this. So I think you guys know that it should, so this is the number of rows and these are the number of columns. So the number of columns of this matrix should match the number of rows of this vector. So it should have 3 rows, and then it's a vector, it's a column vector, so it is going to have only 1 column. So that would give me a vector again, which is 3 cross 1 vector. Okay, so I think you guys might have been familiar with this. So what this concept is like, if you have a 3 cross 3 matrix and a 3 cross 1 vector, of course it has to be a 1 because it's a vector. You would again get a this cross this. So the number of rows of this into the number of column of this vector in the result. So it's a 3 cross 1. And then what is the difference between, or why do we need this? Again, so for example, a 3 cross 3 matrix and 3 cross 1 matrix, in linear algebra, what it actually means is, so this is nothing but a linear combination of the columns of this matrix. It's a very different way of putting in down, but it's a very beautiful way of putting it down. And that's a linear algebra thing. We would not discuss that this video because it's out of scope. Then if we go into it, then we would also need to discuss linear spaces. It's going out of the top. So just remember that the reason we are seeing this is, so it's like you take this column, you multiply it with the first one, then you take the second column, you multiply it with the second one, you take the third column, you multiply it with the third one, and add all of them. That's the matrix multiplication. And when you do that, it's matrix addition or scalar multiplication of each of the column of this matrix, followed by matrix addition, and then that's and then it's a final result that you get. So inside, again, for scalar multiplication of a vector, it's using BLAS. Then for addition, it's again using BLAS, and BLAS in itself is using SIMP. So the reason to put this down is how all these concepts are interconnected. And if you go to do this thing in pure Python, it's gonna be very time consuming. So I'm not trying to encode for this, but try to understand the concept. We are not here to, or like just try to understand that, okay, this is what is the code. The code can be easily generated or made or written down, but the actual concept is that how SIMD works, how BLAS works, and then this BLAS is how it's actually doing things. Okay, so that's how it happens. This is a matrix operation, which is matrix operation is a matrix multiplication. Okay, so this is most important in machine learning. Of course, you have an equation in the back propagation algorithm, which is W x plus b, and then where x are the independent columns, W are the randomized weights, and B is a bias for plus minus of what the results that we get. So it's different topic again, but really believe me, the entire foundation of deep learning AI is just on matrix multiplications, and that's the reason why I am even going into this much depth of why NumPy is even a thing. Like, why did we need NumPy even after having Python in there? So these are the three level of different operations. So simple vector operations, then matrix vector operations, and matrix operations. So BLAS makes all of these faster. We can do all this in Python, pure Python, but it's slow. But NumPy makes it very easy, and NumPy in itself uses BLAS. Okay, so you can see. Let's break this down. So if I do some matrix multiplication in NumPy, it does not use loop. It uses SIMP. Calls BLAS function like dgem, and BLAS splits matrices into blocks depending upon the value of register. Like, it's a 256 bits of register or a 124 bits of register, depends upon that. Then keeps the blocks in the cache, uses SIMP, and then uses multiple cores. Multiple cores is nothing but multi-threading, so that you can actually do the operations parallelly or inside different threads, and then you take the results from threads and then show off them. So that's again another level of another way of reducing the time complexity. So calling decades of numerical optimization research. Yeah. So this is actually true. So this line is a gem. You are indirectly calling decades of numerical optimization research, because building this was not an easy thing. It was completely built in C and C++. So even if today, if you want to build something like Linux, an operating system, C and C++ is the only language. I mean, nothing can beat the fast pace of these languages. So cache blocking is something that it uses. So if you go for new matrix multiplication, this is how you multiply matrices in Python. but the problem is that memory access jumps all over the matrix. You do it element wise, and then you have a lot of time consuming thing and causes cache misses. So you don't have cache. But when you use BLAS, split the matrices into smaller titles. Then there's a CPU cache into which it caches the different blocks that fit inside the CPU cache, and then reduce memory. So memory movement is also reduced, and the time complexity is also decreased. This gives 5 to 20x improved performance. So again, it's a very beautiful thing. Now the last topic of this video is nothing but LAPACK, and this is again the same thing. It is again the same linear algebra thing, where we are trying to perform some higher level of operations that are performed in linear algebra. For example, the board again. Let it down. I think I will need this thing. Get the power. So, for example, I have something like this. So, A x equals to lambda. So this is an equation that I have. I draw a lot of figures inside this, but I'm not used to writing inside this with pencil. So this is an equation which is one of the most beautiful equation. And how do we solve it? We just do this thing minus the x equals to 0. Remember, these are matrices. So this is nothing but a zero matrix, or you can consider this as a vector, okay, of the size of what the x is. Okay. And then you solve this equation, you get the value of lambda. You put in, then you get the value of x. So you either have lambda or x. So this is nothing but, so here the x is called as eigenvector and the lambda is called as eigenvalue. So why is this concept even important, or why is this talk in linear algebra? So let me explain. So if you closely look at this equation, remember the A is a matrix, so you can consider it similar to this equation, or in this way, if you want to consider it according to the spatial arrangement. So let me just try to update this. So you can write this as equal to, then this is a line. So consider that this is a matrix, this is the x vector, this is some lambda, which is what we need to find, and then this is the x vector again. So if you closely look, this matrix is just scaling this vector, because you get a lambda which is a scalar, and then you again get the same vector. So basically, if geometrically I try to explain this concept, what it actually means is, so for example, see, this is my, for example, this is my y-axis, this is my x-axis, and this is my vector x. Consider it is equal to 1 comma, and then after some time this becomes and extends to something 2 comma 4. So if you closely look here, the lambda is 2, because this vector is nothing but something like This is 1, this is 2. Then if I multiply this with 2, so I multiply this with 2, what I get is 2 in here and 4 in here. And this is that same vector which we're trying to understand. So the amazing part is you understood that there's a matrix A with which when I multiply this vector x, which is 1, 2, I get a lambda value. In this case, it's 2, and then I get the same vector, which is 1, 2. I mean, I have already taken the 2 outside, so basically it's 1, 2. So these two vectors are same. This is a matrix which we are multiplying with the vector. So basically, this is a kind of a spatial matrix which is scaling this vector. It's not rotating it at all. It is only scaling it. So when we scale, it's either in the positive direction or either in the negative direction. So if I write -2 in here, it would be in this direction. So similar to what we have this, but in this direction. So it would be -2 and -4. So that would go in here because negative x and negative y. So somewhere here is what it would lie. So this value or this matrix is just scaling it out. And this is a very beautiful phenomenon in linear algebra, because if you think on this by stopping for some time, you would understand that this is, and let me be honest, that this phenomenon is also used in quantum physics or quantum mechanics. How? So just a simple thing. In quantum mechanics, there's a concept called superposition, which says that until and unless you don't see something, that thing is in all the states, all the possible states. So to be more specific, we try to calculate spin of an electron, okay? And it is said that the spin of electron is in superposition. So when we say it's in superposition, what it actually means is this, for example, consider that this is its state, but what it means is that it could be anywhere in between, and actually the values are somewhere in here, like 1, 0, 1 and 1, 0. Those are the actual values. And when I try to calculate its value, you get it? When I try to calculate its value, it comes out to be these eigenvectors, or these eigenvalues rather. So basically, these kind of vectors are called as eigenvectors, and these lambda values are called as eigenvalues. So when you try to actually measure the spin of any electron, it's always going to be the eigenvalues of that vector, of the function that is representing the spin of the vector. And this is one of the most beautiful things. So it is kind of something which does not has any explanation, but it comes out to be that it's the eigenvalues and the eigenvectors. So these kind of operations. So basically, as I explained, that we would have this kind of equation, and the goal is to find these eigenvalues and the eigenvectors. And then when we try to do that, this again involves solving this equation, and then again it involves a lot of matrix calculations, which uses BLAS. BLAS under the hood uses SIMP. So everything is connected. And then the LAPACK thing is something which is used to calculate these kind of harder linear algebra concepts. So you can go through this built on top of BLAS. BLAS handles basic operations. LAPACK handles advanced numerical algorithms. So examples, solving linear equations. So if you go into this thing, so this comes out to be any kind of equation. Maybe it would be a quadratic equation. So you get 2 eigenvalues. Maybe it's a cubic equation, you would get 3 eigenvalues. Maybe it's more fourth root. You may get 4 roots of it. So something to the power of 4, something to the power of 5. So depends. So these kind of equations are solved using them. Okay. Then eigenvalue decomposition, the same thing which I explained. SVD is again a different linear algebra concept. QR decomposition is another different kind of concept. LU decomposition is again a different kind of concept. In LU decomposition, we try to decompose a matrix into a upper matrix and a lower matrix, or upper triangular matrix and a lower triangular. That's LU decomposition as much as I know. But these are all advanced linear algebra algorithms or calculations, and then LAPACK is something that is being used. So why is this even important? Because this is heavily used in all the machine learning concepts that we have. So if you go, there's a concept of PCA which uses this same thing. Linear eigenvalues and eigenvectors. So what we try to do is we try to bring in whatever. So for example, if I have d number of independent columns inside my database or my data set, and then I want to actually compress the same amount of information inside lesser number of dimensions, then I do PC, which is nothing but principal component analysis. And then we try to find where the maximum correlation exists, which in itself uses this eigenvalue, eigenvector concept, which I just explained. So it's like that. So these kind of things, if you go with pure Python, it's not possible. It's not possible. I mean, it's possible, but it's going to take a lot of time, and we would not even. So we would have never reached till models like GPT and Gemini and Anthropic or Claude models, not Anthropic, Claude. Sorry for using that. So this is the end of the NumPy thing. And to summarize all these 3 concepts in one go, so you can visualize the full stack in this way. We write some Python code. There is a NumPy API, which in itself calls a C implementation, which has BLAS and LAPACK inside it. LAPACK and BLAS uses SIMD, and SIMD does CPU vector units, which in itself are nothing but resistors, vector resistors. Then each layer removes abstraction and increases performance. So this is how the people were, the intelligent people were, who made all these kind of things. So this matters in deep learning because it's completely of matrix calculations, a lot of matrix calculations, vector additions, dot products. And to be honest, you know what? Now I explained you these concepts like eigenvalues, eigenvectors. So if you go or you try to learn machine learning, linear algebra, this is the harder part. To understand the mathematics is a harder part because this is the core of machine learning. You could not skip this. But when you go to code all this, there is already a solution. You just see, to be honest, if you go and solve, for example, it's a quadratic equation, easy, 2 roots. It's a cubic equation, a little bit hard. What if it's a power 4 equation? What if it's a power 5 equation? Would you be able to solve it? No, but because of NumPy, it becomes easier to solve. And then this is required because currently we can only deal with 3 dimensions. Human brain can only think about 3 dimensions. We can't think beyond 3rd dimension. We could not imagine 4th, 5th dimensions. But algebraically, everything is possible. And then that's the reason we have these kind of frameworks in Python or in other languages. So training a neural network is calling BLAS millions of times because it has millions of different matrix multiplications, matrix operations. So if you even consider the backpropagation algorithm, it has forward pass, then you go backward, and then you calculate the derivatives of the loss functions, and then you try to decrease the loss into the train. Then calculating the derivatives in itself, again you could not go element wise differentiation. You need to differentiate the entire vector or the entire matrix. It is an element wise operation, but then again you use BLAS for that, so you do it SIMD kind of way and not element wise as we do in Python. So deep engineering insight is that reducing memory movement, maximum caching usage, using vectorized instructions, using multiple cores, using numerically stable algorithms. So BLAS handles till fourth, and LAPACK handles the fifth one, that is doing the numerical algorithms, and SIMD handles hardware parallelism. So these three concepts or these three stuffs work in together to give us the beauty of what we have in the last. So this is pretty much. So if you go, let's copy this down. As I said, that we would just copy the code and not try to write it completely because we are already late. Sorry for that. So here what we are doing is we are making an NumPy array, which is a 4x4 matrix, okay, of random numbers. So random NumPy.random, and this is random numbers, which is a 4x4 shape. Then we are printing this matrix. We are rounding each of its number to 3 decimal places. And then we are performing sublinear algebra, BLAS and LAPACK operations. So here we are finding the determinant. Here we are finding the eigenvalue. So you just look at this thing. It's just a small line of an API. NumPy linear algebra dot eigenvals a dot real dot rounding up again then to 3 decimal places. Then a matrix norm. This is again a different concept. And then SVD, and then printing each of them. So this is a 4x4 matrix, original matrix, rounded to 3 decimal places. Then we have the determinant, which is with this. We have eigenvalues. So look at this. You have 4 eigenvalues. That means it's a power 4 equation that you need to solve. If you go and try to solve this manually, it's a very big deal, actually, to be honest. It takes a lot of time, maybe a half hour, 15 minutes, depends upon how is your mathematics. Then this is the matrix norm, and then this is the singular value decomposition. And these concepts, if you go and do them by hand, you try to do it using your bare hands, it takes a lot of time. But just look at the power of number. 3 things: SIMD, BLAS, and LAPACK. Cool. So that's pretty much. And then real reason. This is the same thing that we discussed before. This is the full picture, and then we have something as a final coding tool, wherein we are again trying to do everything. So we are trying to do addition. The first place we are doing this element wise pure Pythonic way. This is the NumPy way. This is Pythonic. This is NumPy. This is Pythonic. This is NumPy. And then we are trying to calculate the time taken by each of them. So if I run this, sorry for that, try to run this piece of code, then you get the addition, list, NumPy, and speed up. So for the pure Pythonic, it took 15 seconds. Sorry, not 15 seconds, 15 milliseconds. For NumPy, it took only 1 millisecond. For the next part, faster. For multiplication by 2, it took 8 milliseconds. This 0.22 milliseconds, 37x faster. And then sum of all the elements took 1.07. This is 0.11, and this is 10x faster. So you can see NumPy wins everywhere. So this is the reason, the final reason, that why we even needed NumPy and why is NumPy even a thing. Because it's faster. The more fast you are, the more things move faster. So Just imagine if NumPy would have not existed, then there are libraries called PyTorch, TensorFlow. These would have not existed, which uses the core concepts of NumPy to make themselves. And if those would have not existed, LLM trainings would have not exist. If LLM training would have not exist, large language models would have not existed. So, along with GPUs, these things or building softwares which are compatible or which would make proper efficient use of the hardware, of the benefits the hardware is providing you, is also important. So it's not that only hardware part needs to be fixed. You also need softwares which speaks with the hardwares and try to catch up with the efficiency that the hardware is providing. That's what things like NumPy, PyTorch do. So this is the end of NumPy session. Next, we would try to cover. I think I remember that we would just train a neural network purely using NumPy. Next, we would try to do that in the next coming videos. Or maybe even before that, I will try to go for different algorithms. Maybe go for backpropagation algorithm. I mean, before training a neural network, it would be important that we know the mathematics behind the thing that we are even doing. So maybe we can cover mathematics part separately, and then we can move ahead with the neural network training using purely. So I hope you are enjoying these videos, and stay tuned for more such information. It's a very long journey because this is the basics of AI, something which is of course very important. If you understand this, the AI that you use today would also. Thank you again and good night. Bye bye.